Good day and welcome to my YouTube channel. I am Achu Francis Deban. Today we're going to be taking on logarithms, but theory of logarithms. So the theory of logarithms seems a little different from the normal logarithm we know in base 10. So this one deals with other bases other than base 10. So in theory of logarithm, if we define logarithm as the log of n base a, this tells us that the power at which a must be raised to give us n. So in theory of logarithm, it defines that power which the base of the logarithm will be raised to give us the number of the log. So if we, for example, say log 4 in base 2, we are referring to the power at which 2, or the number of times at which 2 can be raised to give us what the log 4. So in order for us to be able to get that, we could easily say we equate it to x. So this becomes 2 raised to the power x is equals to 4. Therefore, 2 raised to the power x is equals to 2 raised to the power 2. Because 4 is the same thing as 2 raised to the power 2. 2 times 2 times give us 4. So if I cancel out this because they are equal, my x is equals to 2. It therefore tells you that the number at which 2 have to be raised to give us 4 is 2. Because 2 raised to the power 2 is 4. So that simply defines what? The theory of logarithms. So we'll be able to look at some examples to determine the various numbers at which their bases can be raised to give us what? Their log. So let's take log 16 in base 2. Alright, now we have the log of 16 in base 2. So we're looking at the number of times 2 will be raised to give us 16. A lot of us can just, by virtue of our understanding of indices, know exactly how to get that, the number of times it will be raised. But we must have to show empirically how that can be determined mathematically. So we say this is equals to what? X. So this is 2 raised to the power x is equals to 16. Now 2 raised to the power x is equals to 2 raised to the power what to give us 16? 2 raised to the power 3 is 8. 2 raised to the power 4 is 16. So which means this is 2 times 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, so it's 2 raised to the power 4 to give us 16. Then we proceed to have, if the bases are the same from exponential functions, which we dealt with earlier on in indices, means we can cancel this out, and our x is equals to 4. It means, therefore, that the number by which 2 can be raised to give us 16 is 4. So 2 raised to the power 4 is 16. So that is it. Let's take another one. Log 32 base 4. Log 32 base 4. So that number which 4 can be raised to give us 32 is unknown. We call it x. So now we can say 4 raised to the power x is equals to 32. Now, no matter how many times I raise 4, I can't get something like having the same basis. I can't bring 32 having a common base with 4. But there is another number which can equate the basis, and that number is 2. And I know 4 here means that 2 raised to the power 2 is the same thing as 4. But it was having the power x, which I can introduce the power x. This is Power's law of indices. When the number is raised to a certain power, which is again raised to another power, that number 2 is said to be in powers, and the powers are multiplied together for final result, which means I have to expand this to get my final result. Now here, this other side, how many times can 2 be raised to give me 32? And that is 5 times. If that is true, I expand this. 2 raised to the power 2 times x is 2x. And this is equals to 2 raised to the power 5. Having 2 to be common, having the same basis, means I can cancel out. Exponential function defines that. So this will go, and I have 2x is equals to 5. If I divide, since I'm looking for x, I have to divide both sides by a number that is close to s, which is 2. And that becomes both sides divided by 2. And this will be gone. My x is 5/2. Or my x is 2 whole number 1/2. Okay, let's take another example. Log 4√2 in base 2. Log 4√2 in base 2. If you remember our sort, where we're instructed to have our variable in a single word sort, in a single root, what do? We have to convert this into what will be in the same root. So although here I have this is equal to x, now I have my 2 raised to the power x is equal to 4√2. Now 2 raised to the power x, to have a single sort, I have to put this in a root form and also square it. That is the only way the value of 4 can be maintained, because the root of 4 is the same thing as 1/2. So if I want to show that this is the same thing as 4, I can illustrate that by showing you here. Say 4 raised to the power 2, the root is the same thing as 1/2. So 2 times 1 divided by 2 is 1. 4 raised to the power 1 is 4. So it means it's the same thing. So doing this does not change the value of 4. I'm still maintaining the same word value, which I should be dealing with. So in that sense, I proceed further. I have √2 here times my √2. So here is 2 raised to the power x is equal to the root of 4. 4 squared is 16 times the root of 2. Now 2 raised to the power x is equal to the root of, according to the sort, I can multiply them, which is 16 times 2, which is 32. Now I'm having 32. I can now remove the root sign to have 2 raised to the power x is equal to 32 raised to the power 1/2. That's the same thing as root. But I know too well that 32 is the same thing as 2 raised to the power 5. So I can say 2 raised to the power x is equal to 2 raised to the power of 5 raised to the power 1/2. And this is 2 raised to the power x is equal to 2 raised to the power 5/2. By expanding this, 5 times 1 is 5 divided by 2. So if I have this, I can cancel this out. The 2 will be gone, and my x is equal to 5/2. So all of this they're taking us to a particular position, because at a point we're going to make use of these variables. When we are done solving our log and get to this conclusion, this position where we think probably we have concluded, thereby we realize that we have to move further, a little further, to understand the principles of log and how they work. So let's take another question. Let's take log half in base 2. Log 1/2 in base 2. So we're looking at the number of times 2 can be raised to give us 1/2. So we equate that as x. So this gives me 2 raised to the power of x is equal to 1/2. From fractional negative index law, I see when a number is raised to a negative index, it is equal to the reciprocal raised to the same positive index. Which means inversely, I can still return this to be 2 raised to the power minus 1. Because if this is defined by negative index, that it is raised to negative, it can become the reciprocal of this number, which is 1/2, raised to the same positive index, which is 1. It means that this is the same thing as this. So I can now bring in this through y, because I want them to have the same common basis, where I can cancel out to proceed. So now I have 2 here and 2, I take this out, and my x is equal to minus 1. Let's take more exercises. Okay, we have log 1/3 in base 9. Log 1/3 in base 9. the number of times it defines according to the theory of logarithm. This is the number of times 9 can be raised to give us 1 over 3. So by doing that, we equate it to x. So this gives me 9 raised to the power x is equals to 3. Okay, let me not spatiate now. 1 over 3 by virtue of what we have. I want to have the same common basis. So I will have 9 to be 3 raised to the power 2. Now raised to the power x, Power's law of indices. When a number is raised to a certain power, which is again raised to another power, the number is said to be in power, so I can multiply them out. So this is equal to this, negative index comes again. This becomes 3 raised to the power minus 1 to have this. So in this other side, 3, I expand 2 times x is 2x, and this is equal to 3 raised to the power minus 1. It means I can cancel and cancel this. I have my 2x is equal to minus 1. Divide both sides by 2. This will cancel, and my x is equal to minus 1 over 2. So, this is the number of times, minus 1 over 2, that this number, 9, can be raised to give us this. Okay, let's proceed. Okay, we've taken... Okay, now let us find the values of x in the following. Okay, before we get into the laws of logarithms, it also have laws, just like indices had its own laws. And the laws are very related, very, very closely related. So we're going to see how that is going to play out at the long run. But let's look for the values of x in the following examples. Log x in base 10 is equal to 4. Log x in base 10 is equal to 4. So this still tells you that the number of times 10 have to be raised in order for us to get x is the same. So this becomes 10 raised to the power 4 is equal to x. That's that. 10 raised to the power 4 is equal to x. And 10 raised to the power 4 is what? So that's a big number. So my x is equal to 10 raised to the power 4, which is probably 10 raised to the power 4 is 10,000. So that's big, 10,000. Now let's take another one. 2 log x in base 2 is equal to minus 6. Log x in base 2 is equal to minus 6. So I only have my 2 raised to the power minus 6. This is equal to x. So my x is equal to 2 raised to the power minus 6. When a number is raised to a negative index, it is equal to the reciprocal of that number raised to the same positive index. So this becomes x equals to 1 over 2 raised to the power 6, which is x is equal to 1 over, I think that should be 64. Let's take another number. Log 16 in base x is equal to 2. Log 16 in base x is equal to 2. So this is x raised to the power 2 is equal to 16. My x raised to the power 2 is equal to 16 is the same thing as 2 raised to the power of 4. So 2 is raised to the power 4. In this sense, I cannot cancel. So I'm going to use, because I have the power here, which is 2. So I will use 4 in this sense. So I can now have 4 raised to the power of 2. That will give me 16, which is the same variable. So if I cancel the powers, which is this, my x is equal to 4. Okay. Let's take one more. Let's go into the laws of logarithms without wasting much time, because this, at least we are familiar with them right now. And through the laws of logarithm, we'll be able to see how we're going to make use of this application. And that's going to really help. Let's take one, please. Now, we have the addition law. The addition law says that log x plus log y in common basis, number 1, log x in base A plus log y in base A. This is the same thing as the log in base of A, because they have the A's, they are common. They are common basis. Open bracket x, y. It means that when I have my log of any number in one base, a common base, another number having a same base, it means I should take a common log, the common base, the log and the common base, one of it, and multiply the numbers. That's the law. Let's take one example and see how that works. Log 4 plus log 25 in base 10. Log 4 plus log 25 all in base 10. So if I have this, according to the law here, I will take the common what? Base, which is 10. So I now have the log in base 10, which is this, open bracket, I multiply these two, 4 times 25. So that becomes the log in the common base of 10, 4 times 25 is 100. So, if you check very well, what we have been doing so far is our ability to be able to resolve variables in this form. When we get to this level, what else do? We equate it to x. To know the number of times 10 must be raised to give us 100. That's what we've been doing earlier on before the laws. So here we have to apply that little knowledge which we have gotten earlier on in the beginning of this class to see how many times we can raise 10 to get this. So we equate it to x. This is equals to x. So come over here. Now I have my log 100 in base 10 is equals to x. So this is 10 raised to the power of x is equals to 100. And this is 10 raised to the power of x is equals to 100 is the same thing as 10 raised to the power of 2. So I can easily cancel this and I have my x is equals to 2. So now that shows that 10 must be raised 2 times in order for us to get 100. So 10 times 10 is 100. So multiplication law, addition law, that is how it goes. Let's take another law, the subtraction law. The subtraction law says, let's clean this and take that. The subtraction law says that the log of x in base A minus the log of y in base A will become, I do the same thing, take the common log in base A, open bracket, x over y. X will divide by y. Don't forget, in division law of indices, when number with equal bases are divided, their powers are subtracted. Here, when they have the same bases, what do? We divide. So it's like the opposite. So if this is true, let's take a practical example. We have 28 and 14 in base 4. The log of 28 in base 4 minus the log of 14 in base 4. So now the law says that we should take the log in base 4 of 28 divided by 14. And when I do that, I have my log in base 4. 28 divided by 14 is 2. So this is not all. So we have to equate it to x. To know the number of times 4 can be raised to give us 2. So let's see the number of times that can be done. So this is my 4 raised to the power of x is equals to 2. Of course, raised to the power of 1. Let's come over here. Now, I want them to have the same basis, common basis. So I will have to break this into Powers law of indices. So as 4 becomes 2 raised to the power of 2. So this becomes 2 raised to the power of 2 is 4. Then raised to the power of x. So this is equals to 2 raised to the power of 1. So this is, by expanding the powers, 2 raised to the power, 2 times x is 2x. And this is equals to 2 raised to the power 1. I cancel out this. I have 2 raised to the power x is equals to 1. I divide both sides by 2. Cancel this. My s is equals to 1 over 2. So the number of times at which 4 can be raised to give us 2 is by half. We raise 4 by half. We're going to get 2. So that's the subtraction law. Let's look at the power law. Let's take this out. So in the power law, it says that when a log x, let me write it down. When we have a log x in base a is raised to the power of n, that the power can be used to multiply the log. So this can therefore become the n multiplied by the log of x in base a. So let's see a practical application of this. That is what the law says. When a log of number x is raised to the power of n in base a, that the power n can be used to multiply the log, which is this. So let's see, take an example. Log 8 raised to the power 3. Log 8 raised to the power 3 in base, let's say in base 2. So this can therefore become, the 3 will come in front, multiplied by the log of 8 base 2. Now, this isn't all. We have to proceed. This is my 3 times. The log of 8 in base 2 become log of 8 in base 2 is equal to x. I have to evaluate what x is. This is equal to 3 times. Here become 2 raised to the power x is equal to 8. 8 is the same thing as 2 raised to the power 3. I cancel this. This is 3 times. My x is equal to 3. My x is equal to 3. So I have 3 in place of x. So this is equal to 3 times 3 is 9. So that's Powers law. We can still take another example to show that. Log 9 raised to the power half in base 81. Log 9 raised to the power half in base 81. So we say we use the power to multiply. So this becomes 1 over 2 multiplied with the log of 9 base 81. Okay, if that is that, this is equal to 1 over 2 times, this is the same thing as log of 9 base 81 is equal to x. This is equal to 1 over 2 times 81 raised to the power of x, yes, is equal to 9. This is the same thing as 1 over 2 times, this is 81, I want them to have the same base, it becomes 9 raised to the power 2, here for 81, or raised to the power x is equal to 9 raised to the power 1, perhaps. So this is equal to 1 over 2 times 9 raised to the power 2x is equal to 9 raised to the power 1. I cancel out this. This is 1 over 2 times 2x is equal to 1. So I'm looking for x. I divide both sides by 2. So this becomes 1 over 2 times, when this cancels out, my x becomes half, times 1 over 2, which is a half. and that is equals to 1 over 4. So that is what Power's law says, and we have to follow it patiently and religiously. Let's take another law. Okay, power of the base. It says that when it is the base that has the power, the reciprocal of this power is used to multiply the logarithm itself. Okay, so the reciprocal of the power. So let's take log x in base a raised to the power 2. Let's clean this. Take log x in base a raised to the power 2. We say when it is the base that have the power, that the reciprocal of that power of the base is used to multiply the log. And the reciprocal of 2 is 1 over 2. So this becomes 1 over 2 log x base a. So let's take example. Okay. Log 16, 2 raised to the power 3. Okay. Log 16, 2 raised to the power 3. So this is the power of the log, the reciprocal of the power of the log, which is 3, become 1 over 3. So this becomes 1 over 3 multiplied by log 16 in base 2. So this is 1 over 3 times log 16 in base 2 is equal to x. And this is 1 over 3 times 2 raised to the power of x is equal to 16. 16 is 2 raised to the power of 4. And if that is true, that is raised to the power of 4, I can easily cancel out. So this becomes 1 over 3 times, this cancels out, and my x is equal to 4 times 4. And this becomes 4 over 3. Okay, let's take one more example on that before we can move out on power of the base. Now we say that another one, log 27 in base 9 raised to the power half. Log 27 in base 9 raised to the power of half. 9 raised to the power of half. Now the reciprocal of the power, which is 1 over 2, the reciprocal of 1 over 2 is now 2 multiplied by the log. So this becomes 2 multiplied by log 27 in base 9. Now this is 2 times log 27 in base 9 is equal to x. And this is 2 times 9 raised to the power of x is equal to 27. 2 times 9, I can say 9 is the same thing as 3 raised to the power of 2, give me 9. Or x is equal to 3 raised to the power of 3 will give me 27. So this is 2 times 3 raised to the power of 2x is equal to 3 raised to the power of 3. I can cancel out this. 2 times 2, if I want to make my x, 2x is equal to 3. Divide this out by 2. So 2 times, my x is now 3 over 2, which is equals to 2 times 3 is 6. 6 divided by 2 is 3. Okay, so we are still talking about the laws of logarithms. Alright, we've talked about the Power's law, addition law, subtraction law. Power of the base is what we're just talking about right now, dealing with right now. So now logarithm to its own base. The logarithm of any number to its own base is equal to 1. That's what they say. So log A base A is 1. So let's see that. How it's true. How true that is. The logarithm of any number to its own base is equal to 1. The logarithm of any number A to its own base A is equal to 1. So let's see how, if we have the logarithm of 10 to its own base 10, how is it 1? So we're looking at the number of times 10 can be raised to give us 10. So we equate this to x. So this is 10 raised to the power x is equal to 10 raised to the power 1. 10 raised to the power 1 is the same thing as 10. So if I cancel out this, my x is equal to 1. So the logarithm of any number to its own base is truly equals to 1. Let's take another one. Logarithm of 1. The logarithm of 1 is equals to, of any number to its own base. Okay, I've said that. Logarithm of 1 to any base is equals to 0. So let's take log, for example, log 10, log 1 in base 10. Log 1 in base 10. So the log of 1 in base 10, let's say it's equals to 0. So this is equals to x if we want to evaluate. So this is 10 raised to power x is equals to 1. Now, we know that our business is to ensure we have common basis. And we are having one now here. And we know that there is a number which we can use to have the same basis that will still maintain the value of 1. It's the same 10. 10 raised to the power 0 is 1. That is 0 index plus. Any number raised to the power 0 is 1. So if I use 10 raised to the power 0, it will still give me 1, which means it's still the same thing as this. So I can therefore say 10 raised to the power x is equal to 10 raised to the power 0 because 10 raised to the power 0 is 1. And by so doing, I have to cancel out the bases and my x is equal to 0. So no wonder they say the logarithm of 1 to any base is equal to 0. Let's please just take questions and see what we get. Let's take log 16 over log 32. Exercises, log 16 over log 32. We have log 16 divided by log 32. So from here, we have our principle of logarithm which states that we can still have log 16 minus log 32. That is true. And if we have that, we can still have, because it's the same base 10, now we can still have this log in base 10. We say 16 divided by 32. We can still have as log in base 10, which is 1 over 2, 1 over 2. 16 going to 0, 1 going to 32, 2 times. And when you do that, you equate it to x. We say 10 raised to the power x is equals to 1 over 2. 10 raised to the power x is equals to 2 raised to the power minus 1. You realize that along the line, we are very unlikely going to have the same base when we use this principle. The principle is perfect, but it doesn't work to the letter. You must understand when you're applying it and see how that goes. When you see the errors are coming forth, you should know where to go or run to. Then you apply another law. This is the subtraction law. It doesn't work. So we can use Power's law to see how that works. Let's go back to Power's law. Now, in Power's law, this is the same thing as log 16 is the same thing as 2 raised to the power 4 over log 32 is the same thing as 2 raised to the power of 5. And according to the Power's law, when a number is raised to a certain power, we can use the power to multiply the log, and that becomes 4 log 2 over 5 log 2. Now the log 2 are the same. I cancel out. And my answer becomes 4 over 5. Yeah, it is achievable. So we must be conversant with the laws that will be able to know how to apply them, how and fastly, how to move. Let's take another example. We have log root 7 over log 7. Log root 7 over root 7 also. Log root 7 over log 7. Let me be sure what I said. Over log 7. Good. So here, we're almost having the same thing, but the only difference is this root. Even though we would have been able to just cancel it, they are both log 7, and we have our 1. So, but then, because of this root, we still know from Power's law that log root 7 is the same as log 7 raised to the power 1 over 2 over log 7. And this, you see, we used to multiply. So 1 over 2 log 7 divided by log 7. The log 7 are the same. So our answer is 1 over 2. Let's take another one. Log 14 minus log 7 in base 4. Log 14 minus log 7 in base 4. So according to the subtraction law, we divide that. So we have log in base 4, open bracket, 14 divided by 7. That is what the law says. So this becomes log in base 4, 14 divided by 7 is 2. And this is not over, we equate it to x. We want to know the number of times 4 can be raised to give us 2. So we now have 4 raised to the power x is equals to 2 raised to the power 1. So this is the same thing. I want to have the same basis. So I have to reduce this to have 2 raised to the power 2 is 4. Open bracket x, Power's law of indices, equals to 2 raised to the power 1. So this is 2 raised to the power 2x is equals to 2 raised to the power 1. I cancel out the 2. I have 2x is equals to 1. Divide both sides by 2. So my x is equals to 1 over 2. Which is half. So let's take some more questions before we proceed further. Okay, log 32 plus log 2. Log 32 plus log 2, I think, in base 4. In base 4. Let me be certain. Base 4. The law says, addition law, when this happens, we should multiply the logs. So I now have the common log, which is log in base 4, open bracket 32 times 2. That is what it says. So log in base 4, this is 64. So let's know how many times can 4 be raised to give us what? 64. So we equate that to x. So this becomes 4 raised to the power x is equals to 64. Here, the 4, I can easily say 2 raised to the power 2. Open bracket, that's 4. With the power here, x, Power's law of indices, is equals to 2 raised to the power 5 is 32. 6 is 64. So this is 2 raised to the power 2x is equals to 2 raised to the power 6. So when I cancel this, I have 2x is equals to 6 divided by 2. So my x is equals to 3. So 4 can be raised 3 times to give us 64. Let's take another one. Okay. Log 8 minus log 32. 6 log 8 minus log 32. In what base? In base 4. Or in base 4. So this is Power's law, I can bring it back here, whatever the value is, and deal with it. But the variable obviously is going to be b. So I have log 8 raised to the power 6, which is this, in base 4 minus log 32 raised in base 4. So my 8, I can now say I bring a common log base 4, open bracket 8 raised to the power 6 over 32. Log in base 4, 8 raised to the power 6 divided by 32 gives us what? 8 raised to the power 6 divided by 32, you got 8192. Wow. 8192. Now, how many times can 4 be raised to give us 8192? That's big. I don't know. So this is equal to x. So I have 4 raised to the power x is equal to 8192. Now, let me try to see that. How many times? 4 raised to the power of 5 doesn't go. 4 raised to the power of 6 doesn't go. 4 raised to the power of 9. Uh-oh, too much. 4 raised to the power of 7. It doesn't. Let's see 2. 2 raised to the power of 12 is 4. Okay. 2 raised to the power of 13. 8192. So 2 can go. So I have to reduce them to the base of 2. So this is 2 raised to the power of 2, open bracket x, is equals to 2 raised to the power of 13. So this is 2 raised to the power 2x is equals to 2 raised to the power of 13. So I cancel out 2. So 2x is equals to 13. Divide both sides by 2. X is equals to 13 over 2, which is 6/1 over 2. 13 divided by 2 is 6 times, remember, 1 over 2. So the number of times which adequately 4 can be raised to give us 8192 is 6.5 times. Okay, let's take another question. Let's evaluate. Evaluate without using tables. Let's say evaluate without using table, so we have to apply the various laws now. Question number 1. 2 log 5 plus log 36. 2 log 5 plus log 36. What again? Minus log 9. Minus log 9. So we want to evaluate this, we apply our laws as usual. So this is log 5 raised to the power 2 plus log 36 minus log 9. This is 25. So it's log 25 plus log 36 minus log 9. So still do the same. Now this is addition. All of them are in base 10, mind you. So whenever a question is given to you and there is no base shown there that it is base 2 or base 3, know that it is in base 10. So let's proceed. Now I have log of, in base 10, open bracket, 25 times 36 over 9. So this is log of what? Let me find out. 25 times 36 divided by 9 is 100. So this is log 100 in base 10. So how many times can 10 be raised? Is 2 times of 4, but that we have to equate to x, and this is 10 raised to the power x is equals to 10 is equals to 100, which is 10 raised to the power x is equals to 10 raised to the power 2. Cancel this, our x is equals to 2. Let's take another question. Okay. Log 27 plus 2 log 9 log 27 plus 2 log 9 minus log 243 minus log 243 all in base 3. This will give us what? So this is the same thing as log 27 in base 3 plus the 2 will go back as power log 9 in base 3 raised to the power 2. The 2 comes back up here minus log 243 in base 3. This is the same thing as log 27 in base 3 plus log 9 squared is 81 in base 3 minus log 243 in base 3. Now apply the laws. Addition law, subtraction law. So I have my common log, which is in base 3, open bracket 27 times 81 divided by 243. Close my bracket. I have log in base 3. I multiply this 27 times 81 divided by 243. It's 9. So this is 9. So how many times can 9 be raised to give us this 2 times? But we equate that to x though. So 3 raised to the power x is equals to 9. And 9 is the same thing as 3 raised to the power 2. Cancel this. X is equals to 2. Let's take more questions. Okay, let's take log root 35 minus log root 7. Log root 35 base 10 minus log root 7. Log root 7 plus log root 2 plus log root 2 all in base 10. So we still do the same thing. We have our log, common log in base 10, open bracket, the root of 35 times the root of 2 divided by the root of 7. So the same, we close our bracket. So log in base 10, open bracket, root of 35 times 2 all over the root of 7. Remember multiplication law in the sort, how you can multiply them, bring them into one place. So this is the log of root 70 over root 7 in base 10. Okay, now I can have this. Yeah, it's possible. Now I have my log in base 10 root 70 over 7, that is division. Then log in base 10 root 10. 7 times 10, 70. So I can take this guy out. as power. Log 10 raised to power 1 over 2, which is this, over base 10. This becomes 1 over 2 log 10 base 10. Log 10 base 10 is 1. So 1 times half is 1 over 2. Yes, that's how it is. Okay, without wasting much time, let's take another aspect. Perhaps there are a lot of things we can do in log, a lot of questions, which with time, you have any question on solve that you've not been able to solve, you can send it across. Let's both solve it together. So, but for the time being, we're going to take substitution and equation in logarithms. So we do substitution and we form our equations in logarithm. And it's a different method of solving log. And we also have evaluation in logarithm. So let's start with the substitution and equation in logarithm. All right, we may just solve 1 or 2 questions and proceed over to solve the other aspects so that we can move forward. So substitution in logarithm involves breaking a given function to simplest form and thereafter substitute its actual value for final evaluation. So it's just breaking down a large number to its basic form, then substituting it finally into the whole equation. So let's start. Okay. It says, given that log 2 in base 10 is equals to 0.3010. Log 3 in base 10 is given as 0.4771. Calculate without using table the values of log 0.72. Without using table, the values of calculate without using table the values of log 0.72 in base 10. Let me be sure. Where is it? Okay, I've seen it. 0.72. 0.72. So first of all, this is 0.72. We have to convert it into a fractional value. So this becomes the log in base 10, 72 over 100. So that is what it means. Now, how? This is 0.72. The real variable here, numbers, is 72 over 100. So it's over 100. So if this is true, I now have log, open bracket, 72 over 100. This in the subtraction law can therefore be written as log in base 10 of 72 minus log in base 10 of 100. So this, can you make this true? So if that is true, I have to look for a way to break down this variable 72 into factors that I can use to get 2 and 3. So that is you just have to go back to your lowest common multiple LCM like we did in solve. So let's take 72 for example. Okay, 2 go here. I think it's 36. 2 go here, 18. 2 go here, 9. 9 go here, 1. That doesn't waste much time. So I can take this as 8. 2 times 3, 8 and 9. So if I have 8 and 9, how can I break this into what will give me 2? 8 is the same thing as 2 raised to the power 3. So I have 2 here. So I can take that. 9 is the same thing as 3 raised to the power 2. I can have 3 here. I have 3 here, so I can use that. So I can use 8 and 9 in this sense to substitute. So let's see how that works. So here I now have log in base 10, open bracket, 8 plus 8 times 9. Let's see, the addition law says that log 8 plus log 9 is the same thing as now log 8, right? 8 times 9. This is what addition law says. So if I have 8 times 9, I can separate them to have log 8 plus log 9. That is the law. So in that sense, I have done this. Then now I have minus log 100 in base 10. So now I can break them down by saying log in base 10, 8 plus log in base 10, 9 minus log in base 10. 100 is the same thing as 10 raised to the power 2. So please let me take the other side of the board. Now log 8 in base 10 can be written as log 8 is 2 raised to the power 3 in base 10. Powers law. I use it to multiply the log. Plus log 9 is 3 raised to the power 2 in base 10. Minus log 10 raised to the power 2 in base 10. So here I have 3. The 3 multiply the power, multiply the log. 3 log 2 in base 10 plus 2 log 3 in base 10 minus 2 log 10 in base 10. Now this is 3 times log 2 here. I'm substituting now 0.3010 plus 2 times log 3 is 0.4771 minus 2 log 10 in base 10 is 1. So let's see what we can do now. 3 times this, 3 times 0.3010 is 0.903. 0.903 plus 2 times 0.4771, 0.9542 minus 2. So I add these two plus 0.903 minus 2 gives me minus 0.1428. So this is my final answer. So that is how substitution works. I think they gave us just one question there. Okay. Okay, let's take, let's just take a couple more. Okay, given that log 2 is 0.3010, we can still use that. Log 3 is 0.4771, which one again? Log 5 is 0.6990. 0.6990. Log 7 is equals to 6990. Log 7 is equals to 0.8451. 0.8451. Or in base 10. Or in base 10. So now another question. Let's clean this with them. Okay, they say, having given us that, evaluate the following without using tables. Log 12. Number 1. Log 12. I think in base 10. Log 12 in base 10. So log 12 can now be written as 12 is, we have 2, we have 3, So if I have 12 to be 4 times 3, which is 12, I have 3 here, but I don't have 4. So this 4 can now become 2 raised to the power 2, where 2 multiplies the power, so we use 4 and 3 in this sense. So now this becomes log in base 10, 4 times 3, which is log in base 10, 4 plus log 3, or in base 10. And this is log in base 10, 2 raised to the power 2, give me 4, plus log 3 raised to 3 in base 10. So this is 2 log 2 in base 10 plus log 3 in base 10. So this becomes, now 2 times log 2, 2 open bracket log 2, which is 0.3010. 0.3010, yeah, plus log 3, which is log 3, yeah, now become 0.4771. So let's multiply 2 times 0.3010 is 0.602. 0.602 plus 0.4771. 4771, which is 1.0791. So that's our first answer, 1.0791. Now, the next one is log 35 minus log 6 in base 10. Calculating this now. Log 35 minus log 6. Log 35 minus log 6, or in base 10. 35 is the same thing as 5 times 7 is 35. Yeah, 5 times 7. So I have 5, I have 7. That will give me 35. So I can now say log in base 10 open bracket 5 times 7 minus log in base 10 open bracket 3 times 2, give me 6. I have 3, I have 2. So now this becomes log in base 10 number 5, log 5 in base 10 plus log 7 in base 10 minus log 3 in base 10 plus log 2 in base 10. Substitute. Log 5 in base 10 is 0.6990. 0.6990 plus log 7, 0.8451. 8451 minus log 3, where are you? 3 is 0.4771 plus log 2 is 0.3010. Okay, let's see. 0.6990 plus 0.8451 is equal to 1.5441. 1.5441 minus go this way, 0.4771 plus 0.3010 is equal to 0.7781. So when I minus this from that, 1.5441 is equal to 0.766 as our final answer. So this substitution and how it goes. Okay, 7 6s. Let's take another one. Log 21 in base 10. Okay. Log 21 in base 10. In base 10. This is the same thing as log 21 is 7 times 3. In base 10, open bracket, 7 times 3, which is the same as log 7 in base 10 plus log 3 in base 10. So this is equal to log 7 is 0.8451 plus log 3 is 0.4771, and this is equal to 0.8451 plus 0.4771, 1.3222. 1.3222. Okay, let's take this one as the last. Log 21 plus log 15. Log 21 plus log 15. 21. Oh, okay. Plus log 15, or in base 10. Log 21, we see that it is the same thing as log in base 10. 7 times 3 will give us 21 plus log in base 10. 5 times 3 will give us 15. So this is log in base 10, 7 plus log 3 in base 10 plus log 5 in base 10 plus log 3 in base 10. Okay, doesn't matter how many times. Log 7 in base 10 is 0.8451 plus log 3 0.4771 plus log 5 0.6990 plus log 3, which is 0.4771. Let's add this all. 0.8451 plus 0.4771 plus 0.6990 plus 0.4771. 2.49. 2.4983. 4983. Okay, let's go down to evaluation in logarithms. The last section is evaluation in logarithms. Okay, let me take this out. This is substitution, and we're done with it. We're done with the laws, and we've been able to apply the laws in answering the basic question that has to do with the laws. We're done with substitution. Now we have to look into the evaluation in logarithms. In evaluation, we say this involves finding the unknown in a logarithmic equation. The unknown. There is always an unknown in this case. It may be linear, quadratic, and so on. So let's say question number 1 says, solve for x, given that 2 log x log x in base 10 plus log 2 in base 10 is equals to 2. Okay, if this is what it is, we're evaluating. So we have to still apply our laws, be it as it may, in one way or the other. So here, the power law can give us this to have log x in base 10 raised to the power 2 plus log 2 in base 10 is equal to, this is 2. Because of the left hand side of my equation has log 10 in it, I have to introduce it here in a way that it will maintain what it is. So this becomes 2 log 10 base 10. The reason why I have to use base 10 is because I have base 10 in this log, so I introduce it here. And I know 10 base 10 is 1. 1 times 2 is still 2. So it has not changed. So I proceed further to have my log x raised to the power 2 in base 10 plus log 2 in base 10 is equal to log 10 raised to the power 2 powers law in base 10. And that is 100. So I have log x raised to the power 2 in base 10 plus log 2 in base 10 is equal to log 10 raised to the power 2 is 100 in base 10. So let us see what we do here. To the left hand side we have plus sign, which is we have to multiply. So I can have log in base 10 open bracket x squared. Okay, let me now use that as my x. X squared times 2 is equal to log 100 in base 10. Now, I have common log here, both are the same. I cancel them out. So I have 2x squared is equal to 100. Let me cross over here. Now, I divide both sides by 2. So x squared is equal to 100 over 2. X squared is equal to 50. Now, to remove this, I square root both sides. So, when I do this, my x is equal to the root of 50, which is not a perfect square. The root of 50 is 7.07. 7.07. Let's take, okay, 0.7, either 1 or so. So this becomes our answer. Okay, let's take another one. Log 2x plus 1 okay, let me take this out. Log in base 10 2x plus 1 minus log in base 10 3x minus 2 is equals to 1. So here again we just do what we know how to do best, perhaps. So I can now introduce the other way now. I have my log in base 10 open bracket 2x plus 1 minus log in base 10 open bracket 3x minus 2 is equal to 1 log 10 base 10. Cross that over, give me the same. So let me start evaluating them both sides. So I now have my log in base 10 open bracket 2x plus 1. There is a subtraction sign, which means I divide over 3x minus 2. Okay. 2x plus 1 over 3x minus 2, all equals to log 10 raised to the power 1 in base 10, which is the same thing. I cancel this and this. I now have 2x plus 1 over 3x minus 2 is equals to 10. I cross multiply. I have 2x plus 1, 2x plus 1 times 1 is the same, is equals to 3x minus 2 times 10. Call it that. So let's expand. 2x plus 1 is equals to 10 times 3x, 30x minus 20. Collection of like terms. I'll prefer the bigger numbers anywhere there are, it's not a problem though. So this is 2x minus 30x is equal to minus 20, which is here minus 1. 2x minus 30x is minus 28x is equal to minus 21. Divide both sides by minus 28. This will cancel. My x is equal to cancel this. 21 over 28, which is 4, 5, 20, okay? 3, 7, 21, 3, 8, 24, 3, 9, 27. Okay, let's leave that 21 over 28. Let's take another question. Okay, 21 over 28, there we go. Evaluate without using tables. Let me check it out. Alright, evaluate without using tables. Log s squared plus 4. S squared plus 4 in base 10 is equals to 2 plus log x in base 10 minus log 20 in base 10. Okay, just want to be sure we're correct. Okay, from here, this have a log, there is and there is, but this doesn't, so it has to be introduced. But whatever is being introduced must still maintain the fact that this number 2 is still the same 2. So I will have my log x squared plus 4 in base 10 is equals to 2 log 10 in base 10, which is 1 times 2 is 2 plus log x in base 10 minus log 20 in base 10. So from here, I presume I've moved it over. Log in base 10, open bracket, x squared plus 4, close bracket, log 10 squared, because this comes up in base 10. Okay, let me just put it one time. In base 10 times x divide by 20. Okay, so this can cancel this. So I have my x squared plus 4 is equal to 100x over 20. Cross multiply. Okay, 20 times this, I have 20, open bracket, x squared plus 4 is equal to 100x. 20 times this is 20x squared plus 80, okay, is equals to 100x. Okay, now from here, if you see this equation very well, you see that we are entering quadratic equation because of the power here is 2. But let me see the much I can reduce them. So this is over 20 over 20 over 20. So this goes 1, 4, 5. So now I have x squared plus, plus 4 is equals to, this is 5x. 5x. I rearrange it. So I have my x squared minus 5x plus 4 is equals to 0. So that is the quadratic equation. So to solve quadratic, I know I have not treated quadratic around, but with time we're going to do that. But we have various methods which we can use. We can use the formula method, we use factorization method, we use completing the square method, we can use the graphical method even. So, but let me use maybe factorization method and see the best I can explain it for the now, because this is not a video for quadratic equation. Okay. So first of all, we're going to multiply the first variable with the last. Let's call it, give us 4. So we are going to look for two numbers. Now when we add them, we have minus 5. When we multiply them, we have plus 4. So this is 4. Let us look for the factors of 4, having multiplied this and this. The factors, the easiest one. If 2 go here, give us 2. 2 go here, give us 1. So we say 2 gives a factor. Then we have 4 and 1 as also what? A factor. Now, in these two numbers, which one has the possibility that when we add, we'll have minus 5? Is this one. This plus this is 4. Yes. This times this is 4. Yes, but cannot give us 5. But this 2, this plus 1 is 5. This times 1 is 4. So this can give us. So if we have spotted a variable that can give us that, 4 and 1, then the next thing we do, come down right here, 4, 1, 4, 1, 4, 1, 4, 1. Minus, 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 plus, plus, minus, plus, plus. This is how you spot in. Although from just the onlook, you just look at it, you can know what the factors are. But for somebody who is learning, you need to know the basics. Use the basics to get what you want. Minus 1 minus 4 is minus 5. Minus 4 plus 1 is minus 3. Plus 4 minus 1 is plus 3. Plus 1 plus this is plus 5. So in all of them, only these two that when we add, only that one we have minus 5. And when we multiply minus 4 times minus 1, we have plus 4. So those two becomes our factors. So we use them to replace this. So we now have x squared minus 4x minus x plus 4 is equal to 0. Okay, from here, I want to factorize these two. And this simultaneous or, alongside. I have my x outside. If I put another x times s will give me s squared. X times 4 to give me minus 4s is minus 4. S times minus 4 is minus 4x. I close my bracket. Now, what you have here must be exactly what you will have in the second bracket. So if that is true, I can just say x minus 4 is what I will get. But now, what am I going to use to multiply with this to give me minus 1? Minus x is minus 1. Minus 1 times x is minus 1. Minus 1 times minus 4 is plus 4. So this becomes my variable. Of base is equals to 0. So now I bring out the variables outside, which is x minus 1. And the ones inside which are the same, which is x minus 4. All this equals to 0. Therefore means that x minus 1 equals to 0 or x minus 4 equals to 0. If that is true, this one crossover become plus 1, or this one crossover become plus 4. So our answer x is equal to 1 or 4. So this logarithm have to take us that far to get into quadratic, and we have to be conversant with the various topics that are associated with what we're dealing with, otherwise we'll be stuck in the process of solving them. So that is what we have there. We're just going to take maybe one last one and call it out for the day. Yeah, I think so. At least we've been able to cover the basic things. So let's take this out. Okay. Now find the values of x if log 10 plus 9x in base 10, close bracket, okay, minus log in base 10, open bracket, 11 minus x is equals to 2. Okay. So what we've been doing so far, we have a log sign here, log here, we have to introduce one here. So we have now log in base 10, open bracket, 10 plus 9x, close bracket, minus log in base 10, open bracket, 11 minus x is equals to 2 log 10 base 10. That log 10 base 10 is 1 times 2 is 2. So it's correct. So we move on to say log in base 10, open bracket, 10 plus 9x minus log in base 10, open bracket, 11 minus x is equals to log 10 raised to the power 2 in base 10. So now I can factorize log in base 10, open bracket, 10 plus 9x divide by, minus sign means divide, 11 minus x, close my bracket, is equals to log in base 10. This is 100, 10 squared is 100, so I can cancel this and this. So now I have 10 plus 9x over 11 minus x is equals to 100. I cross multiply. Okay, if I'm cross multiplying, let's finish it. This times this, so I have 100 open bracket 11 minus x is equals to 10 plus 9x. Okay, my 100 times 11, 1100. So here I have 1100, okay, times this other one minus 100x is equals to 10 plus 9x. Okay, I think we're good here. There is no the power of 2, so there is no quadratic in this case. It's going to be smoother or faster. So here I have minus 100x. This crossover becomes minus 9x. Is equals to 10. This crossover becomes minus 100 and 1100. Okay. I have minus 100 minus 9 is minus 109x is equals to 10 minus 1100 is minus 1090. Divide both sides by minus 109 minus 109. This will cancel. My x is equals to, okay, minus 109. Okay, let's just call it 1090 divided by 109 is 10. So our answer there is 10. Okay, okay, which means, Okay, let me not go into the details of proving it, but that is it. So far we've been able to make justice or do justice to our logarithmic equations in establishing the laws of logarithms, and we've gone through them religiously, and we've also done our evaluation in logarithms, which we just finished right now, and we've done substitution in logarithm. But all things being equal, it is important that we know that this logarithm is somewhat very close or similar to indices. So if we acquaint ourselves with the laws of indices and its applications, then it becomes easier for us to deal with what logarithms. And there are certain other applications like quadratic equation, which we may likely fall into, and even simultaneous equation. If we had proceeded further to solve more, probably would have come across equations that have to end up in a simultaneous manner. So it is important and imperative that we get ourselves acquainted with the various topics in mathematics as we go on day in, day out with math. Do have a wonderful time and enjoy your day.